Swayam Prabha. Digital India. Educated India.
This is where we had stopped our discussion. Now we will go ahead and finish it in this somewhat shorter module. We have obtained an expression for the higher order perturbation correction for energy, and in this expression we have integral psi k 0th V psi k n minus 1th. Let us not bother about V for the moment. V is going to be dependent on what kind of system we look at. Okay. For anharmonic oscillator we will have one form, for say interaction, well, that is time dependent, but for a non-rigid rotor it will be of something else. So, depending on the system we will get different kinds of V. For multi-electron atoms it will be electron-electron repulsion and so on and so forth. So, the problem with this expression is that what it means is that you have to go in steps. It is great that you have one unperturbed wave function in the integral, but the other one is the n minus 1th wave function. So, in order to find out a particular correction term, you must have first worked out the n minus 1th correction term to wave function, okay, in order to find out the nth correction to the energy. So, that is not too happy a situation, and we want to see whether we can derive an expression which can do better than this. So, that is our quest for now, and then we will talk about what is the expression for the perturbed wave function. So, this is our higher order perturbation expression that we have derived. Now, what we will do is we are going to use our old friend turnover rule, and we are going to interchange the wave functions in Bra and Ket vectors. We can do that because V is a real quantity, okay. Remember turnover rule. And why do we do it all of a sudden? Why do we bring psi k, why do we bring the unperturbed wave function from the Bra vector to the Ket vector? Because if you remember, we had said that we have worked out this very important relationship in which I have something like this. I have an expression for this V operating on psi k n minus 1th. Now put n equal to 1, you get 0. Okay. So, that is how things can simplify a little bit. Alright. So, first thing that we will do is we are going to make this V psi k n minus 1th the subject of formula, bring it to the other side, then on the right hand side you will be left with the summation, and you have to bring this h 0th minus e k 0th operating on psi k nth, this term to the right hand side, it will get a minus sign. This is what you have. Now what do I do? See, what am I looking for? I am looking for V psi k 0th. My purpose is to just simplify this Ket vector in the integral. So, I want an expression for V psi k 0th. So, I put n minus 1 equal to 0, because here I have n minus 1. So, I put n equal to 1 essentially. So, when I put n equal to 1, the good thing is that we do not have to worry about the summation anymore, is not it? Summation is from j equal to 0 to n minus 1, okay, n minus 1 equal to 0. So, I mean we are basically summing 0 term, let us not worry about that. We are left with only this term, right, and here also instead of n we are going to write 1. So, I get minus unperturbed Hamiltonian minus unperturbed energy of k, this operator operating on the first order correction to the wave function. Now please remember, this 0th order Hamiltonian minus 0th order energy is not the annihilation operator for the first order correction term to psi k. It is not the annihilation operator for psi k first. it is the annihilation operator for psi k 0th. Please do not get confused here. Okay. These exponents have to match in order for this operator to be an annihilation operator for the wave function. Okay, here they do not match. So, anyway, so we have found this expression. So, next step obviously is to take this expression and plug it back into the integral. So, then this is what we get, the ket vector remains the same, sorry, bra vector remains the same, minus sign comes out. In the ket vector we have h hat 0th minus E k 0th operating on psi k first. Okay. What do I do next? Well, I apply our old friend turnover rule once again. Why do I apply turnover rule once again? Because now I have brought this psi k n minus 1th here. And again if you recall this expression, here we have this, perhaps I should have just taken this, that is a more straightforward thing. We have this expression, we know what happens when this h hat 0th minus E k 0th operates on psi k nth. So, all I have to do is replace n by n minus 1 and I can simplify the ket vector once again. So, in 2 steps I am simplifying the ket vector. Okay. So, we do that, we put instead of n I put n minus 1 here. So, what do I get? h 0th minus E k 0th operating on psi k n minus 1th. You can just look at this expression here relationship here is equal to sum of j equal to 0 to n minus 2, here it was n minus 1, here it has become n minus 2, E k n minus j minus 1th, here it was n minus jth, instead of n everywhere I am writing n minus 1. So, n minus j minus 1th operating on psi k jth, that remains same, minus phi operating on psi k, instead of n minus 1th I write n minus 2th. Okay. Please work this out yourself, please write it out, then only you will understand. It is actually very simple, nothing complicated, it is just like long algebraic expression, nothing else. So, what have I got? I have got an expression, I know what to put now in the ket vector. Okay. So, now I am going to take this and I am going to put it into the ket vector, but then I will use some other trick now. Okay. Since I am going to integrate, I know that while integrating, since this is psi k 1th, this wave function would better be psi k 1th. All other wave functions are going to vanish anyway, right. I can write this sum, there is no problem, and you should write it while practicing. Just write this entire sum, I mean write 2-3 terms and then write the general term. So, when you integrate, you are left multiplying by the complex conjugate of psi k 1th and then integrating over all space. So, except for psi k 1th everything else will vanish. So, the only term that will survive is j equal to 1, okay, first order perturbation. So, when I do that, I put j equal to 1, what do I get? The only energy term that survives is E k, which E k? Nth, right, nth order correction to your energy. So, well, n minus 2th, because this sorry, I made a little mistake, there is minus 1 here. So, n minus 2th. So, I get n minus 2th correction to energy multiplied by psi k 1th, okay, as the first term. Second term remains minus v psi k n minus 2th. Now, we will expand. I have 2 integrals, right. In the ket vector I have 2 terms. So, I might as well write it out as a sum of 2 integrals. The first integral is going to be, I can bring now since there is no more summation, I can bring this E k n minus 2th out of the integral sign, and integral will be psi k 1th, psi k 1th, and well, what is psi k 1th, psi k 1th plus psi k 1th integral psi k 1th v psi k n minus 2th. Okay. So, then this is what I get. This integral, in the first term, well, here I have just interchanged the 2 terms, I have changed the sequence because I do not want to write a minus sign first, but not difficult to see, I hope, that the coefficient of Ek n minus 2th is actually 1 because these are orthonormal. So, I have written 1 there and I have kept this integral and this is the expression. So, what I have got here is that if you have the n minus 2th correction to the energy, then you can find out the nth correction to energy. In fact, it can be shown, it is not really worked out in Pillar's book, but the reference has been given where you can actually find out even the 2n plus 1th correction term to energy by using the wave functions of this L and M. Okay. So, that is the expression, we know how to get the terms for higher order perturbations, how to get the correction terms of energy. Now the question is this, we are using this psi k Lth, psi k mth, how do I find those? What is the expression for psi k qth? There are two ways of doing it, one is by using a variational method, we skip that for the time being because we have not performed a discussion of variation theorem yet, variation method yet, we will do that. For now what we do is we briefly discuss what is called the Rayleigh-Schrodinger method. And Rayleigh-Schrodinger method starts from this expression which we had introduced in one of the earlier modules, psi k nth is equal to sum over I psi I 0th C I k nth. Well, this is just a coefficient. What is the meaning of C I k? The contribution of the ith unperturbed wave function in the kth perturbed wave function, alright. So, you can understand we can write this as matrix equation. I am writing it only for one state, right. If I write it for many states psi k nth, right, psi 1 nth, psi 2 nth, psi 3 nth, psi 4 nth, psi k nth, so on and so forth, then I am going to get a system of linear equations, right. On the right hand side I will get a summation and that can be easily written as a matrix equation. So, this C I k nth, this is essentially a matrix element. Okay. I hope I have been able to make myself clear here. What I am saying is I can write like this, psi 1 nth is equal to psi 1 0th C 11 nth plus psi 2 0th C 21 nth, so on and so forth. I can write something similar for psi 2 nth and I can go on. So, what do I get? On the right hand side I can write this as a matrix, left hand side. On the right hand side I can write it like this, C11 nth, C21 nth, so on and so forth. So, I can write up square matrix and here I am going to have psi 1 0th, psi 2 0th and so on and so forth. Okay. I can write it as a matrix equation. So, these coefficients are essentially matrix elements. This is something that is used ubiquitously in quantum mechanics. Okay. So, please do not get confused if I all of a sudden say that this is a matrix element, and I and k essentially tell us what the position of the matrix element is 1 1 2 2 1 3 3 5 so on and so forth. Alright. So, what I will do is I will use this kind of an expression and plug it into the first order perturbation equation. Here I have not written from the beginning, I have just used it in a more compact, written it in a more compact form. H 0th plus V operates on psi k 0th plus psi k 1th to give us the energy of the corrected energy plus the wave function multiplied by the wave function eigenvalue equation, and from there I can rearrange, and while rearranging I have neglected certain terms because this H 0th psi k 0th will be equal to E k 0th psi k 0th, right. So, they are going to cancel each other. So, this is what we are left with. I think we have done this earlier also. So, on the left hand side I have the annihilation operator, but not for psi k 1th, for psi k 0th. It is not going to annihilate psi k 1th. So, this H 0th minus E k 0th, sorry for missing the hat here, operating on psi k 1th gives me minus V psi k 0th plus E k 1th psi k 0th. So, now I am going to plug in the expression for psi k nth here, putting n equal to 1. Okay. So, I get sum over Cik 1th multiplied by H 0th minus Ek 0th operating on psi I 0th is equal to minus V psi k 0th plus Ek 1th psi k 0th. Okay. I have just taken this and plugged it in here. Now what will happen? I know what happens when H 0th, the unperturbed Hamiltonian, operates on the ith unperturbed wave function psi I 0th. What do I get? Eigenvalue equation, right? I should get Ei 0th multiplied by psi I 0th. So, this is the expression I get. Okay. I get Cik 1th multiplied by Ei 0th minus Ek 0th psi I 0th is equal to right hand side. Okay. It is getting nicer. I have replaced an operator by a value and that too of the value of an unperturbed energy. This is great, it is turning out to be very nice. What do I do next? By now you should have been used to it. I am going to left multiply by a wave function. In this case again I am going to left multiply by an unperturbed wave function, a particular unperturbed wave function. J is not a general index here. Psi j 0th, where j is not equal to k also. Why? Because then when I integrate, then this term is going to vanish. Okay. So, we left multiply by psi j 0th where j is not equal to k and we integrate over all space. So, this is going to give me an integral in which only one term is going to survive, right. In this entire summation, which term will survive? The term in which I is equal to j, is not it? Because this I am going to integrate, I am going to get something like integral psi I 0th, well psi j 0th star psi I 0th d tau integral. So, that will only be equal to 1 when I equal to j, for all other values of I is going to be 0. And what about the right hand side? The second term on the right hand side, when I left multiply by psi j 0, see psi k is a particular value, j is a particular value and I am saying specifically that I have chosen it in such a way that j is not equal to k. So, of course, integral of psi j 0th psi k 0th d tau is going to be 0. So, very nice. On right hand side, out of the two terms one has become 0. What about the first term? This will become some integral involving a triple product, well, involving a wave function and this operator operating on this another wave function. Left hand side simply becomes Cjk 1th multiplied by Ek 0th minus Ei 0th. Is that sure? Is that okay? Instead of I have to write j, okay. I have done that and I have interchanged, okay. I should have written a j here, I am sorry about not doing it here. This is actually j, okay. I think I have made that mistake throughout, later on please correct it. This I, because you understand what is happening here, right. I here is a general index. Now all values of I have vanished except for I equal to j. So, here I should have written j. The other part is simple, I want to take this minus sign to the left hand side. So, I have just interchanged the sequence here, okay. So, sorry about this, this Ek 0th remains there, but this should be Ej 0th, okay, and this integral is 1 for I equal to j. Right hand side I get integral psi j 0th star V psi k 0th. Do I know what that integral is? Not until I know what V is, right. Until now we will leave it at that. So, now I get I have written I everywhere, should have been j, sorry. So, Cjk 1th is equal to integral psi j 0, I will just write it by hand at least. So, this is not I, this is j. This is not I, this is j, alright. So, Cjk first is equal to this integral psi j 0th star V psi k 0th divided by E k 0th minus E j 0th. So, what I will do is I will write this integral here, sorry, I will write this integral here as V j k, not I k, V j k, and this is again going to be j, sorry. Again perhaps for the first time we are using something that we keep doing all the time. We have an integral, we do not know what the form is, we just give it a name. We use indices that help us identify what kind of an integral it is, and we leave it at that. When an opportune moment comes, that is when we try to solve it. Okay. So, I have an expression for Cjk 1th. Okay. So, then you can just take this and substitute here. I have not done it on purpose, I wanted you to do it before I show you the result in the next module. But one important point I want to make is that, see, what is this coefficient? It is the this coefficient is essentially the coefficient for some your wave function, right, is coefficient for some particular unperturbed wave function, alright. So, what we are saying here is that this coefficient is going to blow up when the energies are close. Okay. Remember, we are expanding, we are trying to get the we are working with the kth state. So, when the energies are close to those of the kth state, contributions of state that have whose energies are closer to that of kth state, they are the ones that are going to contribute the most. So, if you plot the coefficient against the index of the wave function I, it will be something like this. So, that is very important, and to summarize, we have learned today over the last 2 modules a general expression for higher order perturbation correction to energy. We have got this expression and we have got it in a couple of ways. We have done it for non-degenerate states, and we have also got, I do not know why I did not write it here, an expression for the corrections to the wave functions. So, now the stage is set for discussion of degenerate states. That is what we will do in the next module.